Continuing our discussion of differential equations and transforms, now we'll look at some solutions to particular linear homogeneous equations. So here are a couple of special cases extracted from the reference handbook. First of all, the first order linear homogeneous differential equation with constant coefficients. So the form of the equation is y prime plus ay is equal to 0. And the solution to this equation is y is equal to c e to the minus at, where the value of c is obtained from the boundary conditions to the differential equation. And we also have the second one, a first-order non-homogeneous differential equation. In other words, the right-hand side here is not equal to 0 in the particular case here where x of t is equal to a step function. And the solution is given right here. So let me do an example then. What is the solution to the differential equation dy by dx plus my is equal to 0? And we can get this from the standard solution in the previous table, but let's deduce it from first principles. So first compare it with the standard equation, standard linear homogeneous equation. Homogeneous because the right-hand side is equal to 0. So comparing those two equations, you see we only have the last two terms appearing there. And if we compare those two equations, we see that in this case the coefficient b1 is equal to 1 and b0 is equal to m. So then we can form the characteristic equation, which in general form is given by this. But again, we only have the last two terms appearing in this particular case because it's a first-order equation. So the characteristic equation then becomes b1r plus b0, but b1 is equal to 1 and b0 is equal to m, so that therefore we have r plus m. And to solve this equation, we set that equal to 0 and solve for r, from which we see that we only have one root, r1, which is equal to minus m. Next we go to our general solution, which is this in its most general form. But however, we don't have these remaining terms here. We only have, in this case, for the first order equation, the first term. So the solution then is equal to c1 e to the r1x, but r1 we already know here, so therefore the solution is c1 e to the minus mx is the solution to that equation, where c is some constant that we evaluate from the boundary conditions. The next special case are second-order differential equations, which have this form: y double prime plus ay prime plus b is equal to 0. And in this case, we can solve this by the same general procedure that we just did, but the specific equations, the solutions to the second order, are given here. And I'll do an example on that. So the example here, which of these is a solution to the differential equation d2y by dx squared plus 2dy by dx equals 0, given the boundary conditions y of 0 equals 0 and y prime of 0, in other words dy by dx evaluated at 0 is 1. Which of these possible solutions is the correct one? Well, first we compare our basic differential equation with the general statement of the linear homogeneous equation, which is this. And in this case, comparing these, we see we only have the last three terms appearing in this equation. And comparing this with this, we see that the coefficients are b2 is equal to 1, b1 is equal to 2, and b0 is equal to 0. So we follow the same steps as in the previous example. Next we go to our general statement of the characteristic equation, which is this, realizing that we only have the last three terms appearing here because now this is a second order differential equation. So that equation becomes this, b2r squared plus b1r plus b0, And substituting these values into here, we find that that is equal to r squared plus 2r, which I can write this way, r times r plus 2, and we want to get the roots of that equation by setting that equal to 0. So obviously the roots of that equation are either r is equal to 0 or r plus 2 is equal to 0. In other words, r equals minus 2. So the two roots are r1 equals 0 and r2 equals minus 2. Now we go to our general solution, c1 e to the r1x, etc. But here again we recognize that we only have the first two terms in this equation will appear in the solution because it's a second-order differential equation. So the solution then is c1 e to the r1x plus c2 e to the r2x, and substituting these values in, we get this equation, which I can write like this. So this is our general solution. Next, however, we can evaluate those constants by applying the boundary conditions. So the first boundary condition I'll apply is this one, dy by dx evaluated at 0 is equal to 1. So I differentiate this expression with respect to x to get minus 2 c2 e to the minus 2x. And then I substitute x equals 0 to evaluate that at 0. And I get that the value is equal to 1. So therefore, solving that equation, the constant c2 is equal to minus 1/2. Next, I apply the first boundary condition that y evaluated at 0 is equal to 0. So substituting x equals 0 into this equation, I get y of 0 is equal to c1 plus c2, from which it follows that, and evaluating that at 0, I have y of 0 is equal to 0, from which it follows that c1 is equal to minus c2, but c2 we already know is minus 1/2, therefore c1 is equal to 1/2. So putting those values into the general solution here, we find that our solution is 1/2 minus 1/2 e to the minus 2x, which I can write a little more neatly as 1 minus e to the minus 2x over 2, and so the answer is B. And this completes our discussion of the solution of linear homogeneous differential equations.